Functions in Rust are declared using the fin keyword, the fin keyword. This keyword allows you to define a function that can be accessed anywhere within the module, and the module is typically just the file that you're actively working in currently. It goes further, we've got our argument types are similar to variables where you just annotate the type of data, right? Is it going to be a string or struct typed or a number and the name of the variable? If the function returns a value, the return value type must be specified with an arrow. So like look at the arrow here, for example. Well, in this case, the arrow is returning a null where basically there's no return type. Additionally, any data that is, so the final expression in the function, now this is similar to like Perl and other languages like that, it'll be used as the return value. Or if you want, you can just use the return statement directly, which is, you know, a little more obvious in that case because you're returning this data. A shorthand, it allows you to just return the final expression in the function. So like the last line, and you do this without a semicolon. You can't use a semicolon. If you do use a semicolon, then it's going to return null, which is very confusing sometimes. So we can write our own function like nothing, right? This is going to be like the most emptiest function ever. So this function will do nothing. All right, let's clean this up here. Okay, so we're going to have a main function that calls our nothing function, and there should be no output without any errors. All right, well, perfect. Okay, and if we wanted to return null, we could do this. We could add this, and then we can also compile that, and that should be fine, right? Yep, all right, perfect, we're good. And we could also explicitly return nothing like this, and that'll work, right? Because it's returning nothing, nothing's a null, so returning null. And if you want, you can add a semicolon here, and it's going to just execute this statement, but then there's another implicit statement that's right here that returns a null, which is invisible. So this is invisible. And so if we were to print that, we can assign a variable to nothing, which returns nothing, which essentially is the null, right? To the nil, and the null, and the none. It's like the nothing, right? These little two, it's like an empty set, basically. Then we print it, and the print is gonna print out null, which is right. That's exactly what we were going for. But if we want to return a number, say like a U32, which is a pretty nice number, I'd say, we would simply return a number there, just like that. Perfect. Nothing is actually now something, and then some. Okay, I think that should work. We should see 42. All right, and we see 42. So we use this arrow symbol here, saying that we're going to return a number, and we return the number. It's super easy. Like, it's really straightforward. Now, looking at the example they have here on the Rust doc directly, we see that we've got a couple of arguments, and these arguments have types associated with them. So we have LHS and RHS are both numbers, and then we can check the numbers and then return data. We can even do a modulus on the data. Oh, it's going to return a Boolean expression. This right here is the last expression state. So we could also say return, and I think return, spell it correctly, and I think that'll do the trick as well. Yes, that works. So these two are the same. Basically, this right here is this. It's a shorthand, which takes a little bit getting used to, because if you put a semicolon here, where you're like, oh, I got to put a semicolon at the end of every single line, this is the one case where you definitely do not put a semicolon. So it is a bit confusing there. Or if you want to be really strict about it and just keep semicolons around, you can use the return statement like this. So just doing a quick code walkthrough real quick before we wrap up, we've got a fizzbuzz2 function to 100, which is going to call this function down here, which is fizzbuzz2, takes a U32 number, creates a range between 1 and the number inclusive, so it should be 1 to 100. We can see the output is 1 to 100 here, yep, and 98, 99, 100. It will execute the fizzbuzz on each number, which is going to be this function here, and then it will print out the data according to the divisibility of each number. It's divisible of 15, 3, or 5, or otherwise. And one last note here, it says that unlike C and C++, there's no restriction on the order of functions that are defined. So you essentially can put functions in all the orders. The Rust compiler will take each function and append it to the table. For example, in some cases, if you define a function down lower, but then you call that function in a higher defined function, you'll get an error because that function's not defined. While the compiler is collecting the definitions of the functions, it hasn't yet run into it. But with Rust, it pre-collects all the function definitions into a function table that can then be used to reference and call upon, even if you're out of order in your call versus definition order. One last thing, a little like neat little tip here. Often when you're programming and you're writing your own code, your own functions, you don't want to just print to the standard output in any function unless it's like a log function. So what you normally want to do is return the data. So you'd want to return the data type, return. You'd want to do something like this, and you'd return like an end string or a string or something along those lines. You want to return the data, and then you would take that data in your upper level function and you choose to print it out if you wanted to. That's like a good pattern for code portability. If you're familiar with object-oriented programming, this is where Rust has got you covered. In Rust, you have the ability to define 2 additional kinds of functions that you're probably familiar with, such as static functions and methods. In Rust, they call them something a little different. You've got associated functions, which are essentially kind of like, a static function where there's no state associated with these functions. They're just functions that you have attached to a structure of kind, like an object. And you also have methods, which are functions that you can write that depend on a pre-initialized sort of struct, and they can access data within that struct. And that's the difference between the two. One is just data. You can kind of use the first one as an initializer, like a new. Now, you don't have to call it new. You can call it whatever you want. This language lets you do it in any direction, so you can even have like a default, say like an origin. So we're defining here a point, a struct, right? So this is kind of like our object. And then we want to add some functions to it. We can add some associated functions which return a point, like a new point itself. So we can return a point itself, like a brand new point. You can also define a function that returns a point based on a set of coordinates. And you don't have to have this. There's some simplification we can do here, and you can do it like that. So now you have x, y. It's going to return a new point based on the data that you pass into it. These are like the static functions. And you don't have to return point. You can return whatever you want. This could just be, like a utility class of sorts where you don't have to initialize it. You just want to, it's sort of like a bundle of functions. But in that case, you could just use the module itself, which is the file name, right? The file itself, which is, it has a reference. And so you just reference the file name and then the function, as long as it's, it's a public function in that case. And so if we're defining a method, that's a little bit different because it's going to sort of necessitate that there's already a predefined instance of the struct or the enum or whatever you've built. You implement, this is how you do it. You implement on, say, for example, we've got a rectangle. Although you can also implement on the point. I don't know why we're going a step further with rectangle, and it's not important. What is important is the function definition. So say you wanted to calculate the area of a defined, in this case, rectangle, right? So we've got a rectangle with 2 points. So we have this and self reference, which gives us access to P1 and P2. So then we take, we destructure P1, which is a point, and we get the XY coordinates for the first and the XY coordinates for the second point, and then we calculate the area by doing a simple math here, getting the absolute value, and it returns a float 64. This is what a method is in Rust. It allows you to access the data within so it requires a memory system. It needs to have state. It doesn't need to have state, but it has access to state if you want it, and if you have parameters. Usually you would have a parameter. You can also calculate the perimeter, which is some math functions, right? It's a little bit different math statements. You need to destructure the first and second points. Okay, you can translate it, which inverts the x and y. So it doesn't return anything, it just mutates. Oh, look at that. So we've got this and self mutable. So we mutate ourselves. Oh, okay, so we are going to translate by an x and y. So if we want to move the box, right? We want to move the rectangle. So we want to move the rectangle a little bit this way and a little bit this way. So we move it this way. So you can see how much you want to move the box. So we add these numbers to the points. That's pretty fancy. And it doesn't return anything. You're just mutating by that. That's kind of neat. Okay, what? Hold on a second. All right, so we are implementing a destroy function on the pair struct. It's a method that consumes the resources of the caller by moving the data through move using destructuring, getting the first 2 points, the x and y, from yourself, and then those two things go out of scope, and essentially it frees the struct. Now that's it's weird. It makes sense because you're moving the data into this scope right here, and then these values are no longer used, so they go out of scope, so the data gets freed. Interesting. I mean, it's pretty clean, although it's dumb. I don't know. I would want something a little more, straightforward. We are using the core mechanics of Rust itself, which is really powerful. Don't get me wrong, it's really powerful. It's just not at all obvious other than, the name of the function. And we're not like explicitly saying free. We're just saying we're letting it go because it's going out of scope. And it is minimal code. It really is. It's minimal code. I do like it. It's just not obvious what's going on. You really have to, if you were, okay, sure, like, let's read this. The function destroy, okay, I see that it's going to, destroy the data, right? It's going to free the data. And then you read the code itself, pair first, second equals self. And then you don't even need to print it. You're done, right? You just do this. You destructure the reference, destructure it without, accessing it through a reference. That's it. That's all you have to do. You just move the data into the scope. And then the Rust compiler will know that it needs to free the data because it's out of scope at that point. It's just not obvious that that's happening. It's just not clear. You go to read the code, even though the function's name is destroy, it's just not obvious. Though good to know. This is really good to know. We want to know this. This is an interesting pattern. So what I'm curious about is, real quick, this here, the pair box, right? So this is, when we say box, this means that we're going to heap allocate these integers, which means that instead of it being stack allocated, which is a lot faster, and then it frees after immediately, we have heap allocation, which means it goes in a completely different memory segment that Rust is going to want to hold on for a long time, basically until you do a free type situation. If we don't heap allocate, I'm wondering this destroy will still work. I feel like maybe probably not, but probably. It worked. I don't know if it actually worked. Let's see. What we should be able to do is make sure that we can't do this again, and then we'll get an error. Is it an error? Yes. Okay. Okay, cool. So then you don't need to heap allocate because we've already moved the data. Okay, that's kind of neat. But it is good to know that you can heap allocate if you so desire by using box. Box is a way to heap allocate. All right, we'll just do a quick walkthrough of the code in the main function, and then we're good to go. So we start here by initializing a rectangle. We're just going to use the structure directly and initiate the rectangle using point origin and then a 3 and 4, so the x and y. So these are floats, so here's the points that we're initializing, float 64 x, y. So now we've got ourselves a rectangle, which takes 2 points. Here's the definition of the rectangle. So we got a rectangle with p1, p2. So we could have created an associated function with the rectangle that will ask you for an x1, x2, y1, y2 instead of doing this, but then internally the rectangle can be represented as it is now with the points. So we're using two methods of initialization here, essentially. Notice how we're using these double colons when we're calling associated functions. These are not methods, these are associated functions, sort of like static functions that are always available that you can use without initialization. So this is how you access those functions. So point origin is going to return a new point at 0, 0, right? Because we've implemented a point origin right here, which returns a point. So here's the point, here's the origin. And we don't have like a self-reference here. So these are associated functions. So now we can print out the perimeter and the area of the rectangle using a dot notation. Now this is the kind of notation that we're familiar with when we call methods on our objects, essentially, right? So we've got a rectangle that's already initialized with 0, 0, and 3, 4, right? So it's going to be a rectangle. We get the perimeter and the area, and we should see here rectangle perimeter 14 and area 12. We can also define a mutable rectangle, call it a square, right? So it's going to be a 1 by 1 square. And if we call translate on our rectangle, not the square, but the rectangle, initialized rectangle from a rectangle initialization, we didn't define that as mutable. So if we try to access this method to translate, to move it by 1 point, right? So our translate function here will add based on your input. So we're moving the rectangle. We try to do that, it's going to error out because we didn't define the rectangle as mutable. So we should see an error here when we execute, we compile. Yep, cannot borrow is mutable. We have to add this. This is where the Rust compiler is, for simple things like this, the Rust compiler like, oh, if you really wanted that, just put this right here. On line 77, just add this like little bit right here. And if we did that, I'm pretty sure that's all we have to do, and then that will cause the compiler to be happy. Now it's good. So since we've already defined our square as mutable, we translate it by 1, good to go. And then we also have another example demo here of a pair. We're saying a box new, which is going to initialize a heap allocated integer. This should be an i32 and a box new i32. And here is our pair, which is a struct this is a tuple. This is a tuple, right? So it's not name value pairs. It's, you know, a list of essentially objects. So we have a heap allocated I32, another heap allocated I32, and then we execute our destroy function, and that destroy function is the weird one. Is where we just essentially destructure, right? We move the data from the struct itself into the scope of this inner function, right? This method, which consumes the scope of these two, the ownership of these two values, and then we're done. We've consumed the data, and therefore it goes out of scope. So it destroys the heap allocation of these two values, and the struct itself, the reference. You can still, I wonder if you can still do anything with it. You still got this pair. You can't access anything to it, but I wonder if it could, for example, let's try one thing really quick. I don't know. I don't think this will work. We'll just do something that's like a null, like a test, I'm pretty sure. So that should compile just fine, all happy and good. Now if we say test, is that gonna cause an error because it's been destroyed? Yes. It's because the self has been consumed through the destructuring. So now you can no longer use pair because it's gone. And I'm sure there's still like a reference to the pair itself to the struct that has been destroyed. However, that will also be freed when the scope exits of the function. In this case, it's the main function, but it could be another function. Either way, you can no longer access it. Any of the methods, you cannot access any of the methods. You should be able to access potentially an associated method where we get rid of that. Maybe. Nope, still not happy with that. So then you have to directly access the struct name itself. That will work fine. So you can still do that, of course. Yeah, that makes sense. So this does its job way better than I thought it would. This is really cool. So this actually will destroy, and the compiler will say it's gone. You can't use it ever again.